We've already used the Biot-Savart law to compute the B field, the magnetic field, around a long straight current carrying wire. Now let's review that quickly and then look at how we can use Ampere's law to do the same thing, but with a great deal more ease. Okay, so for the Biot-Savart law, we looked at a long straight wire like this. Imagine dicing it up into little pieces and then considering the magnetic field contribution at some location of interest from each little piece, each little streak of current right there. So the magnitude of this B field is given by the Biot-Savart law. We know from our right-hand rule, dl crossed with our hat, that our B field at that location points with my thumb out of the page. That's our B field pointing out of the page right there, the dB. And to evaluate that, we've got to look at our cross product here, the magnitude of that cross product, the dl crossed with the r hat. We've got some trig involved there. That gets us this expression for dB. Then we recognize that it has only a z component, and to get the total magnetic field at this location, we have to add up the z components of all the magnetic field contributions from every little bit of wire as x goes from negative infinity to positive infinity. So we set up that integral, evaluate it, and this is the answer that we arrived at. In this simpler picture here with just our wire and our current flowing that way, if we envision one single loop of magnetic field, one magnetic field line here, the strength of the field along that line is given by this function of r, your distance from the wire. So we see the B field dropping off as this 1 over r function. Okay, so that's all recap. Let's see if we can arrive at this same result using Ampere's law instead. All right, so we'll take this view of our wire and rotate it 90 degrees so we're looking straight down on our wire at a cross section of our wire. So here we now have our wire coming out of the page with current flowing out of the page at U. These little dots indicating the current kind of spread out throughout the cross section of the wire, all coming out of the page. And here is one example magnetic field line encircling the wire. It could be like this field line right here from our new point of view. And from our other use of right-hand rule, we grab that wire with the thumb pointing in the direction of the current and our fingers curl in the direction of the B field. So there's the circulation direction of our magnetic field. Okay, let's state Ampere's law. It says that if we choose some closed line integral, if we choose some closed path, then the line integral, the closed line integral of B dot ds along that path is equal to mu naught times the current enclosed by that path. So it's time to choose our path. What we'll choose is a circular path of radius little r that lies right on top of one of these magnetic field lines. So that will be our path right there. And we imagine little steps along that path, little ds's. We're going to choose to integrate in the counterclockwise direction around that path. So our little displacement vectors are all tangent to the path at various points. Those are these guys right here. And what we'll need to do is evaluate that dot product of B dot ds at every point along that path. Since our path lies right on top of the magnetic field line, and the magnetic field vector is tangent to the magnetic field line at every point, then our B field vector at each point will be parallel to that ds vector at every point. So in the dot product here, our angle between those two vectors is 0, so cosine of that 0 is 1, and our dot product simplifies to give us just the magnitude of B times the magnitude of ds, and we've handled our dot product. Now, note from the symmetry that the magnetic field strength should be the same at all points on this path, since they're all the same distance from the center of the wire. So B is the same for all little steps ds, so B can be pulled out of our integral. And we're left with adding up all the ds's on our closed line integral all the way around the path. Add up the lengths of all those little steps, which of course gives us the circumference of the path. So B times 2 pi little r. That equals mu naught times the current enclosed, the total current enclosed in the open surface bounded by our closed path. And that would just be the total current coming out of our wire here. So let's call it capital I. Total current coming from our wire, and divide both sides by 2 pi r. And we get that our B field strength as a function of little r, distance from the center of the wire, is mu naught I over 2 pi r, identical to what we found from the Biot-Savart law up here, but I dare say we got this result with much less effort than it took to get this result. That's the value of Ampere's law. When we have a great deal of symmetry like this, it can allow us to find the B field with much less effort than doing a brute force Biot-Savart law integration up here. So that's one of the ways in which Ampere's law is similar to Gauss's law. It's most useful to us when there's a high degree of symmetry to take advantage of, and nice answers sort of fall out of it when we can utilize that symmetry.